Hello and welcome to lecture 42 of the course Theory of Computation. In the previous lecture we saw Rice's theorem and we have also seen other undecidable languages. So Rice's theorem was a technique or a theorem to show undecidability of a certain type of languages. We had also seen other undecidable languages by using reductions. So in this lecture we will see computation histories. Computation histories is an approach to show undecidability of some languages. In particular, we will use this approach to show reduction from ATM to this language. So since ATM, if we can show that ATM reduces to a certain language, then the language that we reduce ATM to is also undecidable, right? So computation histories is a certain technique or approach to perform the reduction from ATM to the language that we want. Because in some cases we are able to use this approach, right? For instance, one of the interesting cases is the Hilbert's 10th problem that we discussed at the end of chapter 3. That was asked by David Hilbert in the ICM. This was shown to be undecidable using this approach, right? So what is computation history? So computation history is just like a history of computing a certain string by a certain TM, right? So as we already know, configuration consists of the tape content, head position and the state of the Turing machine at a certain point of time, right? So computation history is given, let's say computation history of a Turing machine M on a string W is nothing but the sequence of configurations that M goes through while computing on W, right? So it is written as a series of configurations like this, like C1 hash, C2 hash, etc. hash CL, where C1 to CL are the configurations, right? And these hashes are simply delimiters, like to separate one configuration from the other. So there are two definitions. One is accepting computation history and one is rejecting computation history. Right, accepting computation history is nothing but computation history that leads to an acceptance of a string. So accepting computation history is a sequence of configuration C1 up to CL, where the sequence of configurations lead to the string getting accepted, meaning as per the rules of when does a string get accepted, C1 must be the starting configuration of M on W, meaning C1 should be the starting state followed by the input string W, like W1, the individual symbols of W, and CL must be an accepting configuration, right? Only then it gets accepted. So the last configuration must be an accepting configuration, and everything else must be a valid successor of the previous configuration, right? So C2 should be a valid successor of C1, C3 should be a valid successor of C2, C4 should be a valid successor of C3, and so on till CL should be a valid successor of CL minus 1, right? So all the moves should be valid moves. Such a sequence of configurations is called an accepting computation history. So I want each configuration to be a valid successor of the previous one. The starting configuration should be the correct starting configuration, and the accepting configuration should be an accepting configuration. Similarly, we can define rejecting computation history, where everything is the same. Rejecting computation history is defined exactly the same way, just that instead of CL being an accepting configuration, we want CL to be a rejecting configuration, right? So these are the two definitions. What we will just now, for our purposes of this lecture, we will only be using accepting computation history, right? So what we will show in this lecture, or at least show the outline of in this lecture, is a language that we have referred to a couple of times in the past. The language is ALL-CFG. ALL-CFG is asking, given a context-free grammar, does this grammar generate all possible strings? Right. Does it generate all the strings over the terminal set sigma? Right. So this problem happens to be undecidable. So you may recall we showed that we assumed ALL-CFG is undecidable, and we showed that EQ-CFG is also undecidable because you could reduce all CFG to EQ-CFG, right? But we had we had just stated that all CFG is undecidable, and now we'll see the kind of sketch of the proof that all CFG is undecidable, right? So it's an undecidable problem given a grammar, given a context-free grammar, to determine whether this generates the set of all strings possible over the terminal set. Right, let's see why. So we will reduce ATM to all CFG complement. Okay, we'll reduce. So if I reduce ATM to all CFG complement, if I reduce ATM to all CFG complement, this implies that all CFG complement is undecidable. But that also implies that all CFG is undecidable, because if a language L is undecidable, its complement is also undecidable. If L complement is undecidable, then L is also undecidable, because if you can decide the language L complement, you can just flip the output yes to no and no to yes to get a decider for L. So if all CFG is undecidable, all CFG complement is undecidable, there is no way for all CFG to be decidable, right? Because you can flip the decider's output to get a decider for all CFG complement, right? So this implies that all CFG is undecidable as well, right? And the reduction from ATM to all CFG will use computation histories. So let's see how it uses, right? So given M and W, the ATM instances, does M accept W? That's what we have to decide. What we will do is, given the ATM instance M and W, we will construct a context-free grammar, or equivalently a PDA, right? Context-free grammars and PDA, they're equivalent, right? They both recognize the class of context-free languages. This grammar or PDA will generate all the strings which are not an accepting computation history of M or W, right? Which are not, that's also important, which are not an accepting computation history of M on W. So it will generate everything which is not an accepting computation history, right? So which means, so it's a very it's slightly twisted. Suppose M accepts W, right? Then it will not generate the accepting computation history of M on W. It will generate all the other strings, right? The grammar will generate all the other strings. Suppose M does not accept W. So if M does not accept W, there is no way for it to accept W, which means there is no accepting computation history at all, because only if M accepts W can we have an accepting computation history, right? Because otherwise it cannot be valid. So if M does not accept W, the context-free grammar will generate all possible strings, right? It will generate everything, because there is no accepting computation history. So by design, it is supposed to generate all strings that are not an accepting computation history, right? So if M does not accept W, it will generate all the strings. If M accepts W, it will generate all the strings with the exception of the accepting computation history. So when M accepts W, the grammar will not be able to generate all the strings. But when M does not accept W, the grammar is going to be able to generate all the strings, right? So let me define formally ACHMW, right? ACHMW is the set of all accepting computation histories of M on W, right? So it's a set of all strings Z, where Z is in delta star. So delta means delta includes the input string gamma. It also includes the tape string. It also includes states. It also includes hash symbols. Everything that comes in the tapes or in the computation history, right? So any string that is formed out of delta, which is an accepting computation history. So ACH contains all the strings that are an accepting computation history of M on W, right? So this is same as what I just said. MW is an ATM, right? If and only if M accepts W, right? Now, if M accepts W, the accepting computation history is not empty. If it accepts, then there is an accepting computation history. If it does not accept, there is no such thing. So, accepting computation history is not empty means the complement is not everything, right? So, the complement of accepting computation history is not the set of all strings possible, right? Which means the grammar that generates this ACHMW, okay, so maybe to be more precise, the grammar that generates this, maybe I'll just the grammar that generates this ACHMW should not be in all CFG, right? The grammar that generates ACH complement, right? Which means the grammar, again here also the same thing, the grammar that generates this should not be in all CFG means that it should be in the complement of all CFG, right? So that is the reduction. Okay, so maybe I'll edit this. That's the reduction. If MW is in ATM, M accepts W, which means there is an accepting computation history, which means the complement of ACH MW does not contain everything, and hence it is not part of all CFG. So, and if M does not accept W, there is no accepting computation history, and the complement of ACH MW is all the set of all strings, and hence the grammar that generates it is part of all CFG, right? So this gives a reduction from ATM, right? From given MW we are constructing the grammar, right? So it is a reduction from ATM to all CFG complement. Given an instance of ATM, we are giving an instance of all CFG complement, or given a yes instance of ATM, we are giving a yes instance of all CFG complement, which is a no instance of all CFG, but yeah, right? So now what we need to show is to construct a grammar that generates ACH MW complement, right? This grammar, the grammar that we refer to here, we need to build. To complete the reduction, we need to build this, right? So just to summarize, we want to reduce ATM to all CFG complement. We use computation histories. If M accepts W, so we build a grammar that generates all the strings that are not accepting computation history of M on W. Okay, we build a grammar that generates all the strings that are not accepting computation histories. So if M accepts W, then the grammar cannot generate all the strings because there is an accepting computation history. If M does not accept W, then there is no accepting computation history, which means the complement of ACH can generate potentially everything, right? So it is a member of all CFG. That is the reduction. And now what remains is to show the grammar, right? Show the grammar that generates the complement of accepting computation histories of M on W, right? So this part is where we are not going to get into full details because the details may be quite technical. So I just want to go to the high level points, and the details is not that hard. It can be worked out, but it may be too boring or too detailed to kind of go through all of the details, right? So we want a grammar to generate strings in the complement of ACH MW, right? So how can a string not be an accepting computation history, right? All such strings we need to generate, right? So there are four possibilities. First, the string is not even of this. So we want the computation history to be denoted like this, right? This is our desired form for the computation history, right? Configurations starting from the starting configurations to the accepting configurations, separated through valid transition and separated by delimiters hash symbols, right? So perhaps the input itself is not given in this format. It is not a properly formed input. The string is not a well formed computation history. It cannot be read or interpreted as one. In that case, it is not an accepting computation history, right? So this maybe it does not have a hash symbol, or maybe it does not end with the hash symbols, or maybe between two hash symbols there is no state, it is not a valid configuration, or maybe there are two states, right? So all of this is an example of not being well formed. This is actually something that can be checked by a DFA or a regular language, right? It's a regular language because you are just checking whether every hash follows, between every two hashes there is a state and all that, right? Whether it starts and ends with a hash. It's actually a regular language, right? So again, I'm not getting into the detail of how you can check it, but it should be straightforward to see that it's a regular language, right? Okay. So in that case, it's not an accepting computation history. The second case is maybe it is well formed, meaning it starts with hash, ends with hash, and it has C1, C2, etc. Okay. But okay, maybe I just missed a small thing. When I say starts with hash, I think we need this. Right. It has to be this form, I think. Maybe it does. It does look like a proper computation history, but let's say it does not start correctly, meaning the first configuration is not the starting configuration of M on W. It is a configuration, but it is something else. So the starting configuration of M on W should be looking like this, where QS is the starting state, and W1, W2, etc. is the string W. So is the first configuration equal to this? If not, that is another way why Z is not an accepting computation history. This is also easy to check. All we are asking is the first configuration equal to something? This also can be checked using a DFA. Third possibility is that it is a properly formed computation history, but it does not end correctly, meaning the last configuration is not an accepting configuration, meaning the state between the last two hash symbols is not the accepting state, right? So it is not the accepting state. This also can be checked easily using a DFA, because we just have to go to the last two hashes and check whether we remember the last states seen and check whether the last state seen is an accepting state. This also can be checked using a DFA, right? So this is also easy, not that difficult to see. So we have covered it, the string being well formed in the sense of a computation history. It's starting correctly, meaning C1 is the starting configuration. Ending correctly, meaning the last configuration is an accepting configuration, right? Then the final way in which the computation history may not be a valid computation history is if at some point, so we have C1, C2, C3, there is a sequence of configurations. At some point there is some I such that Ci plus 1 is not a valid successor of Ci. There is an I such that Ci is not a valid successor of Ci plus 1 is not a valid successor of Ci. Meaning there is some part where this subpart Ci plus 1, Ci hash Ci plus 1 is not a valid successor. So if there is such a thing, then it is again not a valid accepting computation history, because somewhere you started correctly, ended correctly, but somewhere it is not a valid successor, right? So how do we do this? We non-deterministically guess an I, right? So we have a PDA. So far we just said that everything else can be done by a regular or a DFA, right? So this part requires a PDA or a context-free grammar. We can non-deterministically guess an I for which Ci plus 1 is not a valid successor of Ci, right? And then we check whether this does not happen, right? And then we use a PDA, like once we guess an I, we use a PDA to check whether this is not a valid pair of configurations. Meaning, what do I mean by not valid? Ci plus 1 is not a valid successor of Ci. This can be checked using a PDA. So again, details, I'm not getting into the details, that's why I called it a proof sketch to begin with. But the idea is this. So one good exercise is, there is a problem 2.22 in the book. So I'm reproducing the problem here. So set of all strings, it's a language called C, which is of the form x hash y, strings of the form x hash y, where x and y are from 0, 1, such that x is not equal to y. Right. So I'll tell you the idea for C. So one way to do it is, you guess that if x and y are not equal, you can guess that they may differ in the kth symbol. Right. There are three possibilities. So one is that or two possibilities. One is that x and y are of two different lengths, then they are immediately not equal. So maybe there are three possibilities. One is that x is longer than y. Two is that y is longer than x. Three is that x and y are of the same length, but at some point some symbol differs, meaning maybe some kth symbol of x is not the kth symbol of y. So what you can do is, you can guess some k. I'm just addressing the third part, right? So you can not deterministically decide which path to pursue, right? So you guess k. So to guess k, you just keep pushing symbols into the stack. Okay, so at some point, let's say after pushing, let's say k symbols, maybe k is 10 symbols, you look at the 11th symbol of x, you remember it, and you go to the hash, right? And then you start popping out the stack when you are reading the symbols of y. So you pushed 10 things into the stack. So the first 10 symbols of y are going to be passed by just pushing it. We are not going to compare or anything. This is just used as a counter, right? And then when we come to the 11th symbol of y, we will see that the stack is empty. You can put a dollar or something to identify that. And then you try to remember what you saw earlier and see whether the 11th symbol of x is the same as 11th symbol of y. So you guess which position to, so you not deterministically decide which position to compare. Till that point, you push things into the stack and use that as a counter to get to the same point at y. Right. So this is how, and then you accept if the strings are different, if the 11th symbol is different or the k+1 symbol is different. The same ideas kind of, so maybe this is something that you can try working out, this problem C, right? And the ideas for checking Ci hash Ci+1 is not valid is similar. Just that now that we are not dealing with x not equal to y, we are dealing with two configurations where Ci+1 is not a successor of Ci, right? So earlier here we said x should not be y. Here we are saying Ci+1 should not be a successor of Ci. So earlier it was equality. Here we are saying not a valid successor. So if you write the, let's say this is Ci, this is Ci, this is Ci+1, right? So if you write it like you have some strings, and so if you write two successive configurations, you see that the configurations don't change all that much. Only the part around the head changes. So the head is here, right? A, Q, B, because Q indicates the state, and this means the head is pointing to B. Here that is replaced by RAC. So only these symbols around the head changes. So you can check. You may have to remember more details because 2 or 3 symbols may change, and you don't know where the head is going to be while processing. So you have to not only determine which position K that you are going to check, but you also have to remember couple more states, a couple more symbols, not just so in the case of C, we said we remembered just the k+1 symbol. Here we may need to remember more symbols than just k+1, right? So that is the main idea here. We need to remember more symbols because this transition that I have written here, this happens when delta QB is RCL, meaning here the state is Q, it is then the head is pointing at B, and the move here is that state goes to R B is overwritten by the symbol C, and then the head moves one step to the left, right? So now this A has moved over here, right? So this you can see, this A has moved over here, the state has moved one step to the left, and B has changed to C. So that is the result of this move. If it was a move, the head moved to the right, it would be slightly different. But the point is that whatever is the move corresponding to the particular configuration, the move, the next step, we'll have to identify that and make amends in the or make changes in the, or we'll have to construct the context free grammar appropriately in order to track that. So that is the main idea of the proof, that all CFG is undecidable, right? Maybe I'll just quickly summarize. So an accepting computation history is a sequence of configuration starting with starting configuration, ending at an accepting configuration where each transition is valid, right? So to show that all CFG is undecidable, we reduce ATM to all CFG. So given an ATM instance, which is a pair MW, we will build a grammar, right, that generates all the strings that are not an accepting computation history, right? And so if M accepts W, this grammar cannot generate all the strings because there is a valid computation history. If it does not accept W, it can generate everything. So MW is an ATM if and only if the grammar does not generate all the strings, or if and only if the grammar is in the complement of all CFG. That's how we get the reduction of ATM from all CFG. And now, how do you build such a grammar? There are four possibilities. The first one being we want to generate ill-formed strings, which is not a configuration. Second one is it does not start correctly. Third one is it does not end correctly, meaning it's not an accepting. The last configuration is not an accepting configuration. The final thing is what we required some work, and that too we just gave the high level overview and not the entire proof. That there is some I for which Ci plus 1, the I plus 1 configuration is not a valid successor of Ci, and that we said that we can do it by using a PDA, but I am kind of alternatively, like interchangeably using PDA and CFG, right? So if there is a PDA, we can use a CFG as well. So we keep track of some like where to compare using the stack, and then you remember the last couple of symbols read so that you know how to adjust yourself, right? And if you read the book, this part of the proof is written slightly differently. This last part, the book uses something where alternate configurations are written in the reverse manner. So you have C1, then C2 in reverse, then C3, then C4 in reverse, or something like that, right? So that's also correct. This is slightly different, but this is also a valid approach, right? So that's how this proves that we can build a CFG that generates all the strings that are not an accepting computation history, and that completes the reduction from ATM to the complement of all CFG. This means complement of all CFG is undecidable, which also means that all CFG is undecidable, right? And that is the main thing that I want to cover in this lecture. I'll just briefly describe one problem before the next lecture, but then this will be the last lecture for this week. This is going to be a rather lighter week, but I just want to give you something to think about. So I'll just state the main thing that the first thing that I will discuss next week. So this problem is called post correspondence problem, and the reason for discussing this problem is that so far the problems that we have seen, the undecidable problems that we have seen, are of the type like, is there a Turing machine that accepts this? Is there a Turing machine that recognizes an empty? Like, it's a very abstract kind of situation, right? So far the languages that we have seen that are undecidable are rather abstract. This is a very simple problem that is very easy to describe. You can even tell it to some third standard, fourth standard school going child, right? And the problem is so easy to describe, so I just want to describe the problem. So we'll see the proof in the coming week. So given some dominoes, so the problem is this: given some dominoes, we want to see whether can we list them in such a way that there is a match. Match means can we list them in such a way that the top string and the bottom string are the same. Okay, so maybe it's best described through an example. So let's see this. Okay, so there are 5 dominoes. First one is AB in the top and ABA in the bottom. Then BA in the top and ABB in the bottom. B in the top and AB in the bottom. ABB in the top and B in the bottom. A in the top and BAB in the bottom. Now I claim that the following listing here, this constitutes a match. So as you can see, then I am using some dominoes more than once, right? And it looks like I am using all the dominoes at least once, but even that is not necessary, right? We don't need to use all the dominoes, and I am allowed to use dominoes more than once. Yeah. So let's see. So if you read the top string, it is ABA BAB. So here if you see ABA BAB, so it's the same string. Then the rest is ABB ABB, and from here it's ABB ABB, right? So now we are up to here in the bottom and we are up to here in the top. The rest is BABB B. Oh no. Okay, I think there is a small error. It's ABB divided, the bottom is B. Right. So let's do it again. So AB AB AB. The first 4 dominoes top part is AB AB AB. First 2 dominoes bottom part is AB AB AB. So now up to 4th in the top, up to 2nd in the bottom. Then ABB ABB up to 6th in the top. ABB ABB up to 5th in the bottom. So right now the rest is BABB and BABB. So so if you read the entire top string, it is the same as the bottom string, and this is what we mean by a match. So the question is this: given an instance like this, is there some way, or can we tell whether there is such a match or not? That is the problem. Given an instance, is there a match or not? Meaning, match means is there a way to write the dominoes in some order with possible repeats. We don't have to have repeats, but we can have repeats in such a way that we get a match. This is the problem. So it's a very simple problem, very easy to, simple meaning simple to describe. However, this problem turns out to be undecidable. Right? It's such a simple question, you can tell it to some school going child, but this problem turns out to be undecidable. So this is in sharp contrast with what we have seen before, right? The other problems is in ATM, does this Turing machine accept, does this halt, is this regular, and like Rice's theorem, they all seem very abstract things. But here we have something which is very clearly, easily described and very concrete problem. And surprisingly, this problem turns out to be undecidable. So maybe you can just try to come up with strategies, and you'll see that you'll not be able to create an algorithm for this, right? So that may give you some indication of why this is indeed. So there is no general algorithm. That's what it means to be undecidable. Of course, in some cases by inspection you can figure out a match. In some cases by inspection you can rule out a match, but there is no standard, clearly well-defined approach that will lead us to clearly saying yes, this has a match or this does not have a match. So the question is, given this instance, we have to figure out whether is there a match or not, yes or no. But it is an undecidable problem. Okay. So that completes this lecture number 42. This also completes week 8 lectures, right? So in week 8, we have seen reductions, we have seen reductions. We defined reductions. We saw undecidable languages using reductions. Then we saw Rice's theorem, which was a template result that could show that many languages are undecidable, like many languages that fall in that framework. Then we saw computation histories and saw the high level overview that all CFG, or not high level, not that high level, but somewhere medium level overview that all CFG is undecidable. And then I stated the post correspondence problem. So it is called post correspondence problem because it was invented by a mathematician called Post. Right? So post means that. And I said that we'll see the undecidability of post correspondence problem. It's also sometimes abbreviated as PCP next week, and also maybe applications for this. And that's all I have in lecture 42 and also week 8. So see you in the next week.